right. So where we last left off, we were talking about list as our first real data structure. And so we're going to first look at its abstract data type, right? So we talked about how to reason about an abstract data type in more formal logic semantics with axiomatic specification. That's what we did last time. And now we're actually going to see how does this work in code, right? So in order to create a list, right, we want to create a list interface, because that's the abstract data type, right? So for a particular data structure, its abstract data type is embodied in Java by an interface. And then we want to create a concrete implementation, an actual implementation of list, and that's a class that's going to implement list, right? So So I have defined in the example code for this lecture in the package A9 list, right? We have the interface, right? So this is the Java embodiment of a list of T as an abstract data type, right? So that's what the interface is. There's a syntax here that we haven't encountered before, but basically it's the generic syntax. You may have used it, and in fact you did use it for assignment 3, hopefully, when you created an array list of integers, when you read all your, or a list of integers using array list as its implementation, and read all your numbers in order to create your histogram. So here we have, so it's one thing to use a generic interface or a generic class. It's another thing to write a generic interface or a generic class. But basically the idea here is that in declaring the interface list, we put angle bracket and then a placeholder for a type. In this case, I'm using the capital letter T, and then close angle bracket. You can actually create interfaces or classes that are essentially generic with respect to one or even more placeholder types by simply providing a capitalized letter. I don't actually know if it has to be capitalized, but it's traditionally capitalized for each type that you need a template for. So the idea here is that when I actually use this interface, I'm going to actually specify a particular type for T, right? But in writing the interface and in reading the documentation about the interface and understanding the interface, we're going to do it with respect to this placeholder. But then when we actually use it in real code, we'll actually have to provide a real type name for T. But we can understand this as everywhere we see a single capital letter T, that stands in for whatever type name is provided by the user of this interface. So a list of type T, so a list of T's, whatever T is going to be, list of strings, list of string arrays, list of integer with a big I. The only restriction is it has to be a reference type. We can't say a list of Boolean with a small b, because that's a value type. But for every value type, int, char, boolean, Java provides us with a built-in reference type that represents the same kind of information and will automatically convert from one to the other when we need it to. So it's not that much of a restriction. But basically, we can understand a list of strings, T will be string when we actually use it. So the idea here is that the method size of a list of T will be able to return how long's your list, right? The method isEmpty will return true or false whether or not the list is empty or not, right? It has more than 0 elements. The method clear is going to remove all the elements. The method and doesn't return anything. So it kind of resets the list. The method contains says, and then we can see here, we know that we'll say, does it contain this particular element? What's the type of the element? It's T, whatever T ends up being, right? If it's a list of strings, then contains will expect a string to be provided as, does this list of strings contain this particular string? If it's a list of something else, if it's a list of scanner objects, if it's a list of positions, it's a list of triangles, if it's a list of points, then T will be understood correctly presumably as the appropriate type when it gets used. But when we write it, right, and when our authoring of this interface, we can specify T wherever we understand, this is going to be the same type as whatever the person who's using this interface indicates is the type of the list when they actually use it. So if I give you a T, then you can tell me back true or false, does this list contain that element? If I give it, the next one is find. Find basically says, OK, give me an element of type T, and I will look through this list and find whether or not, find the index where this element occurs in the list. And if I don't find it, I'm going to return -1. Right? So that's another method of this list. We have add. Add is going to add elements to the list. And you'll notice that we have two different forms of the add method, right? We have one form that basically takes only a single parameter, a actual element of type T to add. And then the semantics there, if you read the documentation, says, oh, that adds it to the end of the list, makes the list one longer, puts that element at the very end. And then another form says, add given an index and an element T. That version of add is going to insert the element that I provide at that position in the list. And presumably that index position has to be a valid position. Has to be some value between 0 and size. Not 0 and size -1, but 0 and size. And the reason why it can be size is because if it's size, it just adds it to the end and extends the list. So we're usually used to, when we work with arrays, of thinking of the valid indices as being between 0 and the length of the array -1. For list, which is a different kind of data structure, that has a size that can grow, the valid indices available for adding an element is 0 to size. So 0 to size -1 will put it into the appropriate spot in the list, and then push anything that's past it to, down by 1. And then size as an index is 1 after the last thing that's already in the list. And so if we indicate size for index, then it puts that's valid. That's OK for adding an element. Now, what we can't do is say size +1, right? That should be an error because that's out of bounds. Okay? Similarly, remove also has two forms. Remove says, oh, if I give you an element of type T, go find it and find that element in the list. And if you find it, go ahead and remove it. Take it out of the list. The list shrinks by 1, and I'll return true or false. I'll return true if I found the element and I was able to remove it. And I'll return false if I looked in the list and that element isn't even in the list. In that case, the list remains the same because you didn't find the element you were asked to remove, and I know whether or not the list changed or not, because if the remove returns true, I know, aha, I found that element and the list got shorter by 1. Or it returns false, and then you know, that element didn't actually exist in the list, and the list is unchanged. The other version of remove, instead of taking the element that you want to remove, takes an index that you want to remove. In this case, the valid indices go from 0 to size -1, right? Because we need to be able to, we're indexing into some existing element in the list, and the existing elements in the list go from 0 to size -1. So if I provide you with an index of which element to remove, and it's a valid index, then I will remove that element, right? Shifting down any elements that need to be shifted down so that the indices move down by 1 for everything that's above that index value, and the entire size of the list goes down by 1. And this version of remove actually returns the element T, the element that was removed. That's why the return value, the return type for that second version of remove is of type T. All right. Then, right. And then finally I have get. right? That makes sense. I want to be able to retrieve something. Again, here the valid indices go from 0 to size minus 1, and the list remains unchanged because I'm not removing or adding, but I do retrieve the element t the element that's at that index and return it, and that's why the return value for the get method has type t. And then finally, I have this other a method called set. And set basically takes a valid index, right, from 0 to size minus 1, and an element t, and it replaces whatever was at that index with the element provided to the method as the second parameter, and it returns the element that it replaced. So whatever was at the index, at that index in the list gets taken out of the list. This new element that I passed in takes its place in the list, so the size of the list doesn't change, and then the old element gets returned back to whoever calls it. Okay? And so this is a very typical kind of definition for list and its operations. You might see, in the documentation for list as defined in the Java collections framework, it actually has many more methods that do other things, and some of those methods do the same things that we specified here, but might not have exactly the same name. But for the most part, this captures the spirit of what it means to be a list. And not all of these methods have to be there in order to make this list useful, right? In the end, we really only need to be able to create a list that's a constructor of some implementation of list, and we need to be able to insert into the list, and then we need to be able to probably remove an index, and we need to be able to retrieve an index. Those are probably the 4 fundamental things that we need out of a list. Probably also size. We probably also need to be able to retrieve its size to know how big the list is, right? So not every one of these methods is absolutely required for the list data structure, right? Certainly the canonical methods are, and we know what a canonical method is. That's the set of methods that are required to create any given list. We know for list, that is the constructor and insert, right? And then the other ones are just things that make this list data structure useful. Okay. Any questions about the methods I've chosen to include in this interface that defines our list in our little example here? Yeah.
So what's the difference between add and
So add and set. Add will push the element into the list and move everything down. Set replaces the thing at that same index and takes what it replaced and returns it. So if I say set, I'm not making the list any bigger, right? It's the same size as it was before I said set, because I'm taking an existing element and replacing it with a new element, taking the old element and giving it back to you. Whereas add, if I add at the, so if I say set the fourth, if I set index 4 to be, let's say this is a list of numbers. If I say set index 4 to be 5, right, or make it a list of strings so I don't have numbers going everywhere. If I say set the list, the index 4 of this list of strings to be the word dog, then presumably there's already an index 4 string in the list already, and whatever that string is gets replaced with dog, and then that string gets returned back. Whereas if I say add at index position 4 the word dog, then whatever was at 4 becomes 5. And then whatever was at 5 becomes 6, and then all the way to the end of the list. And it gets bigger, right? Yeah.
Even though new is one of your canonical operations, you don't have to put it.
Right, exactly. So that's the difference between like a theoretical, understanding of a data structure, of an abstract data structure or abstract data type using axiomatic specification and its embodiment as Java code, right? In Java code, we don't list the constructor in the interface because the constructor is part of a specific implementation. That's right. Yes? No. So a method is canonical only if it's absolutely required to create every possible version of list, right? So the only things I need to create every possible version of list is some sort of constructor and the ability to add something, right? I can take, and you can give me, you can say, give me a list of strings that is, kitten, dog, puppy, baby, and just using new in the constructor and add, I can do that, right? But all the other ones are kind of non-canonical because they're not absolutely required in order to create any given list. Your question? Okay, so that's going to be our interface, right? So now let's think about how we're going to implement this. Okay? So there are two main approaches for implementing a list, right? One is going to be storing the elements in an array. So here's where we're going to make a very clear distinction between list, which is a data structure, an idea, an abstraction, right? And array, which is a specific language feature, right? So list is an idea that we can implement in a number of different ways, right? And we'll see one particular way of doing it, right? An array is a language feature that says, please carve out a very specific size of memory. It's never going to shrink. It's never going to grow. And it just provides me with a consecutive set of, a consecutive ordered kind of set of elements that I can address, right? So when I say new string array in Java, it actually goes into memory and carves out, like I have to tell it exactly how big it's going to be. I want a 5, I want a string array of size 5. I want a string array of size 10. And whatever that size is, it goes into heap and finds, enough memory that's consecutive, in memory to store 5 references to a string or 10 references to a string. And the array allows, I can index into that consecutive string of memory, that consecutive area of memory, in order to index into the 0th, 1st, 2nd, all the way up to the length of the array minus 1, and I can set them to null or point them to some string or whatever, right? So array is a low-level, implementation-specific kind of feature, right, or kind of fundamental language feature that Java provides for me to create a piece of memory that represents a sequence of values, okay? Be they integers or string references or whatever, right? Now, we're going to use that, right? So arrays are very useful, and one of the ways we might use the array is to use it as storage for our implementation of list, right? Our list is an idea. It's an abstract data type that is defined entirely by its operations and the axiomatic specification of how those operations combine with each other and what they mean, right? So a list grows and shrinks, and I can think about the a list through rigorously by examining it via by kind of modeling it via axiomatic specification, right? That's what we did before. Now in our code, we want to actually create something in Java which is a list, and we can do that using arrays. Okay? So that's the difference between a list and an array. A list is a very powerful data structure. An array is a very specific thing. It is a continuous bit of memory of a certain length that can be indexed and with values set. And that's what an array is, right? So one way to create a list, to create something that implements a list, is to use arrays, right? Another way to implement a list is to use what's called a linked list, right? And so what we're going to do today is we're going to go over the implementation of list using arrays. And what your homework is going to be creating an implementation of list that uses a linked list. And at the very end of today, I'll explain how a linked list is supposed to work without showing you the code, and then you're going to go off and try to implement it. And we'll discuss it a little bit more on Tuesday as well. Okay, so right. So the first thing we're going to do, right? So now we want to implement lists, right? And we're going to try this first strategy by storing the elements of the list in an array and resizing that array as needed, right? Because remember, our arrays can't, we have to decide how big they are at the beginning, and then once they're however big they are, they can't change. So the way we're going to use arrays in order to implement list is we're going to start off with an array that's, I don't know, some initial size, and then, have an understanding that my list can grow up to that size. And then, by using the elements of the array as the places where I'm going to store my list elements. But my list will keep track of how big the list is, and that's going to be independent of how big the array is, right? Obviously, the array has to be as big as the list, but presumably it's going to be a little bit bigger so that the list can grow, right? At some point, the list might grow to the point where it's already using all of the elements of the array that we're using to store the elements. Then it's going to be on our implementation to recognize that situation and resize that array. Basically create a new array that's bigger and copy all the stuff from the old array to the new array and start using the new array for our storage, right? So that that's all going to happen underneath the covers of our implementation, right? So the user of the list won't have to know about that, won't know it's happening even, but our implementation of list has to be aware of that limitation of the array, because once it's filled, in order to make the list even bigger, we need the underlying array that we're using to store the list elements needs to get bigger also. And we'll see that in a bit. The other way to do it is to use what's known as a node structure, where every element is stored in a structure where the element is in the node, right? The value of the node is the element, and it also has a pointer to the next node, which is the next thing in the list. And that's why we call it a linked list. And we'll see what that looks like at the very end. But for today, we're just going to concentrate on an implementation of array list. So when you have a when you have a data structure that you're trying to implement or express in Java, the first thing to do is to define the interface to the data structure, right? Take that data structure and provide and define the interface for how that data structure is supposed to work. That's essentially expressing the operations of the ADT into the interface. The only operation we don't have to put in the interface is the constructor, because in Java, constructing a specific implementation is part of the class, not the interface. But all the other operations on the data structure we put into the interface, like we just saw, right? The next step of implementing a data structure in Java is to think about which of these operations can be written entirely in terms of the other operations in the interface. Because those operations we can implement as default methods of the interface. In other words, if we think about if we can find a way of implementing one of the interface methods as entirely using the other interface methods, then we don't have to know anything about the details of a specific implementation. We can simply provide a default implementation in the interface where and use the other interface methods to provide the implementation in the interface without having to put it into our concrete implementation. So what we're going to do is we're going to take a look at sorry, I'm echoing. I'm kind of shouting. Sorry. We're going to take a look at our list. Okay. So look at. I'm going to give you a moment. Pair up or confer with your neighbor. Take a look at all of these methods and try to think about which ones we can implement without having to know anything about the implementation details, just by using the other methods of the interface to implement one or more of these operations. So the first thing is to do is let's identify which operations can actually be implemented using the other operations, right? And it's definitely more than one. So I'm going to give you a couple minutes to think about this. and then we will confer. So talks amongst yourselves. Identify which of these can be written entirely with respect to the others. Okay, so before we go to that, I'm going to mix it up a little bit. Let's take the participation quiz now. So if you go to Sakai, there should be a little participation quiz. Now, and everyone who's at home who looked and said, oh, there's no quiz today, they're screwed. All right. So there's a quiz 2.6, should be open. Take it at your leisure. It's open for the next 10 minutes, or until 4:10. There's only one question. Okay, so continue to take the quiz if you still need time on it, but in the meantime, who has an idea about which of these can be implemented, as one of the others? Any takers? Which of these can be, which of the methods can be implemented as, oops, no, that's not what I want. I want this. No. Do I? No. What do I want? I want this. Nope, that's not what I want either. What do I want? I want, oh, fine. I'll just use a box. Okay, so any ideas? Any suggestions? Yeah. Size? Okay. Well, interesting. So you think that we can implement size entirely by all of these other ones? Like which other methods would you use in order to implement size? I don't see how using any of the other methods is going to tell me the size of the list. Yes?
Clear, you could use remove.
Okay, so clear, right? You could implement clear as removing all of the, the existing things until the size is 0. Sure. So, that's absolutely true. So I can do that. So in fact, I can implement it right here. I can say default clear. How would that work? Well, while maybe, is not is empty, right? So as long as there's something in the list, I'm going to remove whatever is at index 0, right? That'll do it. Yeah, sure. Yeah.
So, get, I guess you could do it multiple times, get size.
So get is supposed to actually retrieve an element. So getting the size won't work. Yeah.
You could use find to make contains.
So find can be used in order to figure out contains. Absolutely, right? So here I can say default, right? Contains. I'm going to give somebody else a chance here. I'll give you the chance here. How would I use find in order to implement contains?
You go through the list, and if find is true, then contains is true.
Right? So if I try to find an element, if I say find element, then what's the result of find according to the documentation? It's either going to be an index or -1 if it didn't find it. So if I have to say true or false, does this list contain the element, I can say find element and then compare that to what?
Like say if it's not -1, then return true.
Right. In fact, I could just say return is find not equal to -1. That works, right? Find will either be -1 if it didn't find it, or 0, some valid index if it did. So if it's some valid index, it won't be -1. So it'll be something that's not -1. Something that's not -1 does not equal -1. That expression is either true or false. It's true if it's not equal to -1, so I can return it and that it contains. Otherwise, it's, if find element is -1, that means it's not in there. So -1 does not equal -1. That's a false statement. And so that expression is false, and it gets returned. And that's exactly right. A nice little one-line thing for find. Good. Anybody else? Anything else? What about add? Think about that. I think, a hint here is you can use one to do the other. Yeah. Now let's look at the two forms of add. The first form of add is going to add the element at the end. The second form of add adds the element at a specific index. And there is a specific index for the end, right? What's that? Size. So if I wanted to implement the first form of add in terms of the second form of add, I could do that. I could say default add element t, right, or element of type t. I could say, just add at the current size the element. Any others?
I have a question.
Yeah.
What's the benefit of using a default method if you have another way of getting it?
So what's the benefit of providing this default method?
Yeah, like why would you use that over
Using this?
before? Yeah.
Yeah, so, right, that brings up a good point, right? So when we have multiple versions of the same method, that's called overloading. Actually, I have a slide on that next. And in Java allows you to define the same method more than one time. And you don't have to, but it's a matter of providing convenience to your user, right? It could be that adding to the end of the list is a very common operation, right? So instead of having your user have to say add size the element, right? You just provide another version which is quick and easy, which is it's going to add to the end, right? So you're right. because we have that second version, we don't ever really have to have the first version, because anybody who wanted to add to the end could have written that one line of code in order to add at the end, right? But by providing that first version, it's just convenient if that's a common operation, so that the person who's using it, right, the code that's using it, doesn't have to do it themselves, right? Yeah. Yeah.
You could use the size to get is empty.
Yes, is empty can be implemented as size. It looks a lot like the contains. And I'm going to give you a chance to give me the line. What is the line of code here? Well, somebody said it. Speak up. Return size double equals 0, right? There's an expression that takes size, compares it to 0. That'll either be true or false. If size is 0, then that expression will be true, and is empty will return true. If size is not 0, then that expression will be false, and is empty will return false. All right, so we've size we decided we couldn't do, is empty we could do, clear we could do, contains we could do, find. Actually, it turns out we can even do find, right? And the reason why is because remember how I said that every type has an is-a relationship with the special object type, object with the big O, right? It's the universal reference type. It turns out that this is related to an object-oriented principle called inheritance, which we're not going to really look at in this course. You'll kind of learn that in 301 when you take it in the fall. But it turns out that the equals method, that same equals method that string has, it turns out every object has an equals method, because just like object with a big O is the universal reference type, there are certain methods that are defined for all objects. And one of those is equals. Every type knows how to compare itself to another object. Every object knows how to compare itself using equals to some other object. Strings do it by comparing it character by character if the thing you're comparing to is another string. All the other object types, or many of the other object types, do it just by comparing their references with double equals to see, are we exactly the same object? But whether or not there is some higher order semantic definition of equals or not, every object type has an equals method and can say, true or false, I am equal to some other object. And because of that, we can also do find as a default method, because we can simply say, OK, if I want to find this element, I'll just go through my list as a for loop, maybe. So for integer I equals 0, I less than however long the list is, I plus plus. Then go get the element at each position. I know it's of type T because this is a list of type T. So T E equals get I, right? I'm using the get method to retrieve each index in the list. And then I can say if E dot equals the element, the other element, then aha, I found the thing I'm looking for, and I can return true. And if I get through the whole for loop and I didn't find it, I'll simply return false. Oh, I'm sorry. We need to return the index. I can return I, which is the index where I found it. And if I get through the whole for loop and I never find it, I can return -1. Okay? One version of add was implemented with the other version of add. Remove. Can we do remove? One of these versions of remove, can we do that in terms of other methods? I'm going to tell you that the answer is yes. So now you have to figure out which version can be done as a default and how. Once you think you got it, yeah. Is empty just tells me true or false. Are there things in the list or not? But close. There's something else that will tell me where something is. We just did it. right? So we can use find in order to find the index of what we're looking for to remove, and then use the other version of remove to remove that index, right? So here, this version of remove says you give me an element that you're trying to remove from the list. First, I'll find it in the list. If it's not in the list, well, then I return false. I didn't find it. There was nothing to remove. But if I do find it, then now I have the index of where I found it, and now I can use the other version of remove, which will remove my index in order to remove remove that particular element. So this one also can be done as a default method, right? I can say, like, the index of this element is wherever I find it, right? And if the index is -1, right, because that means I didn't find it, return false, and otherwise remove the thing at that index. This version will give me back the element. I don't really need it, so I'm not going to store it anywhere because I just need the effect of removing it. And then I can return true. I did find it, and I did remove it. Now, all the other ones can't be done, right? All the other ones require knowing exactly how things are being stored and to manipulate the array, or otherwise needs the implementation details. However, if we actually no, set we could do. Yeah, this one we can do. I'm going to give you a minute to think about it. If somebody thinks they have it. Now this time, I'm really not going to code it for you. If you think you have it, and you think you can tell me what the code is, it's not too hard, then I will, yeah. Yes, exactly. So you could add it at the index that you want it to. You know that's going to push everything over. And then you can remove the one that got pushed over, which is the index +1. Exactly right. And you can actually do it the other way around, too. You can remove the thing at index I first, and then add it back at that same index. It doesn't really matter. Right, so we could do this one as a default. Now, to be really, really, good about it, I would, do my defensive programming first. I would say, if index is less than 0, or index is greater than or equal to size, right? Then I have to throw a new runtime exception, index out of bounds. Okay, so that's fine. But once I know that index is good, then I can do exactly what you said. I can add at the index the element I'm trying to add, right? And then I can remove the index +1. I know it'll work because I know that the original index was legal, and that when I added this element at that index, whatever used to be at that index was pushed over by 1. So I know removing index +1 will work. Now, set is supposed to return the old thing that was in the old spot, and remove gives me back the thing that was removed. So I can just simply return what I removed, and there I go. Yeah, absolutely. That'll work. Okay? So already, we have implemented most of list entirely with respect to other methods of list, right? Even without having to know, are you a linked list, are you an array list, or exactly any of the implementation details. So your first strategy for implementing a data structure should, after you've created the interface to reflect the API of the data structure, think about whether or not how much of this you can implement with respect to that interface so that you don't have to do it when you actually implement the actual data structure in a class, right? Because now, anything that implements list, most of it is taken care of, right? All right. So I was going to sit here and type the names of all the methods that you guys identified, but we'll do that. I'll update the notes some other time. But let's see here. Right. Okay, so now once we have defined our interface and we've done as much as we can to implement the various parts of that interface using other parts of that interface, now we need to create a concrete implementation. So like I said, the strategy we're going to take is to use an array of objects in order to store the elements. Now, here's the thing. We're going to write this thing as a generic, right? So we're going to have, just like our interface, angle bracket T, angle bracket. And so just like that, in our class, we're going to have angle bracket, public class, list impl, or whatever we call it, implements list. And we're going to also have angle bracket T, angle bracket. And we can use that placeholder for the type of thing that's being held in our list wherever we need to. But there is one limitation of Java, which is when I'm writing a generic class, or when I'm using generics, right, I am not allowed to create an array of the placeholder, right? So when I'm implementing a generic, I can't say, I need an array of t's, whatever that ends up being, equals new array of t's, whatever that is, of some size, right? You would think that that would be allowable, right? But and I never really understood why. It has to do with how Java is implemented in the JVM and something called type erasure. And like, if you take compilers, you'll learn all about it, right? But for our purposes, you just need to know that that's not allowed. You can't make generic arrays of some placeholder type. But because object with a big O is a type that every class has an is-all relationship with object with a big O as a type, then what we can do is we can create an array of objects with a big O, and that array, right, is okay because we can put anything we want in there because every type has an is-all relationship with object with a big O, and so it doesn't matter, right? So so that's how we're going to create our array in our implementation, right? The other thing, so we need to have some storage. We need to have an array where we're going to store our elements of the list. Now that storage, right, is an array, so I have to decide how big it is in advance, and then later on I can create a new array and swap out my old storage for a new storage that's bigger if I need to make it bigger and copy everything over, and that's exactly what we're going to do. We'll see that, right? But the storage I have is going to have a certain length. The array is going to have a certain length, but this list that I have, that's going to have a different length. So the size of the list, it depends on how many times I've called add, right? I mean, how it's been used, what's been added to it, what's been removed to it, and it grows and it shrinks. So I have to keep track of the size of the list separate from the length of the array that I'm using to store those elements, right? So the array is always going to be bigger than my list. It kind of has to be. If that's my storage for the list, then it has to be at least as big as my list. But it's probably going to be even bigger because I don't want to be resizing my array all the time. So I'm going to make it, kind of bigger than I need it at first. And then once I run out of room, I'll remake it, copying over the old stuff into a bigger array. But I'm not going to make a bigger array just by one. I'll say, oh, well, if I already filled up this array, then I might as well make an array that's even bigger. And so, so the length of the array is at least as big as my list, but might be bigger. So I also have to keep track of how much of that array, which parts of that array are valid, like, how big my actual list is. So I'm going to need to keep track of the size of my list, right? And we'll resize the array to be bigger as needed, okay? So let's do this. So the way we do this is there we go. Right? So here we have here's our interface. Now we need a class that implements this interface. So I'm going to say, okay, give me a new class. And I'm going to call it my list, or my array list, who knows, yeah? Of type T, okay? And, right? And my array list of type T is going to implements list of type T, right? So that's the interface it's going to implement, okay? Great. Now, the second thing I need, right? First I declare my class and the interfaces it implements. Great, I've done that. The second thing I need to do is decide what are my fields? What data do I need? And from that last slide, we said we needed two things. We needed an array of objects for storage, and we needed the current size of the list, right? So principle of encapsulation tells us create our instance fields and make them as private as possible. So I'm going to have a private array of objects that are my elements, and I'm going to have a private integer, which is my current size. Okay? Now the next thing I need is a constructor. When I create a new list, a new myArrayList, right, I need to be able to initialize these fields. So we're going to have a constructor. The constructor always has the same name, right? It should be public, and always has the same name as the class. When we're creating classes that are generic, that are generic with some type T, the constructor, when we declare it, we don't need the angle bracket part. We just use the name up to the angle bracket part. I'm not exactly sure why, but that's if I try to say this, that this is my constructor for creating a list, it won't work. See, it'll give me this error. But it's fine if I just take this T out, right? So here's my constructor. When I create a new array list, I need to initialize my fields. So the first field I need to initialize is my elements, right? That needs to be an array of objects that I can store my element T's, my elements of type T in. And I have to decide, okay, how much storage do you want? Well, I mean, I could say, every time I create a list, I'm going to create 1,000,000 things in my array. Yeah, sure, you won't have to resize the list very often, but you'll be wasting a lot of storage, right? So here it's kind of a trade-off. You don't know how big this list is going to be. It depends on who's using it. They might put 2 things in it. They might put 200 things in it. They might put 2,000,000 things in it. Now, you're going to, as they work with the list and they add things to it and remove things to it, you're going to keep track, and you're going to make that array bigger if you need to. But for now, we have to decide what our initial size is. Well, let's just pick some reasonable size like 10, right? Or maybe, if we're really good about it, we might want to create a static variable, private static final int, right? So this is going to be a named constant, which is, a init size, or how about a init length, so that we don't confuse it with size. Let's say 10, right? And so that's just a named constant, so that's good programming practice. You don't want to have magic numbers in your code. If if there is some constant, then you want to define a name for it, and so that way you can what the purpose of this constant is, and if you need to change it, you can change it in one spot, and it'll change everywhere you use it. So here I'm going to say, okay, my elements is going to be a new object array of size init length, right? So that gives me some storage space. Great. When I create that, all of those elements are going to be null, which is fine because I don't know what's going to go in it yet. And more importantly, what's the size of my new list? Anyone? 0, right? It's not an int, right? Because I haven't put anything in the list yet, right? This is the difference between the size of the array that I'm using for storage and the length of the array I'm using for storage and the size of my list. When I create a new list, it starts off empty, right? So the size of the list is 0. I haven't put anything in it. Now, the size of my elements array, that is currently 10, but that's okay. I just need it to be something other than 0 so that there's some space for some elements, right? And what I'm going to do is as I add things to the list, I'm going to keep track of how big the list is getting, and if the size of the list ever becomes the same as the length of the array, then I know that I've run out of space in my storage, and I will do something in order to create more storage. Okay, so there's my constructor. Now you'll notice that this myArrayList has a little red squiggly line on it. The nice thing about Eclipse is it understands that if you said myArrayList is going to implement list, and here's our definition for list, Eclipse automatically knows, hey, if that's true, if you really implement list, then you need to provide implementations of everything that's in list that doesn't already have a default implementation, right? The default implementations are good enough, right? So it's not going to demand that you provide a implementation of something that there's a default for, but for everything that we couldn't implement as a default, that's missing. And so the cool thing is that if I just hover over the red square, or the red squiggly line, one of the quick fixes that comes up is add unimplemented methods. And if you select that, Eclipse does a lot of work for you. It automatically generates all of the methods that you still need to provide, but they don't really do anything, right? I mean, so they're kind of stubs. They're fake. And now it's on you to go through and find all these to-dos and replace that code with the stuff that actually implements things, right? So for example, here is the size method on my list, right? What's the code, the appropriate code for implementing this? It's one line. Return size. That's right. Right? Whatever the size is. Okay? Here I have add. I need to add to a particular index that particular element. Okay? So the first thing I need to do is to make sure that the index is legal, right? And so I have some defensive coding here. So I say if index is less than 0 or index is greater than size, right? Because remember, size is legal for add because I can add at the size index. That just means extend the list by 1, right? So that's throw new runtime exception. That index, right? All right, now I know that the index is okay, right? Now I need to put it into my array at the right place. But what could go wrong? What do I have to be careful of? Right? What I want to do is something like this. I want to say elements, right? That's where I'm storing everything. At that index, right, is going to equal this element. But what do I need to make sure, what do I have to do with the things that are already in my array? If I have a list of 3 strings, right, 0, 1, and 2, and then I add something at index 1, what happens to the thing that was already at 1 and what's already at 2? It has to be pushed over, right? So the first thing I have to do is push everything over, so that I can put my thing there, right? So this is what I want to do in the end, but if I just do that, I'm going to overwrite whatever was at index. So I need to make sure that starting at index and going to the end of the list, I need to push everything over, right? Well, if I have an array, right? So if I have my array and the first 3 items have my things in it, and these are null, so this is null, 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 but this is something, this is something, this is something, and now I'm adding something here, right? I need to take this and put it here, and I need to take this and put it here, right? And then that will make my, push everything over, and then I can put whatever I'm trying to add in this spot, and now my list is 1 bigger, and I've pushed everything over. So because I have to push everything over, it's easier to start at the end and pull everything back until we get to here, and then have a hole, if you will, that you can put your new item in. So to do this, I'm going to start at the end of the list. So I'm going to go backwards. I'm going to say for int I equals size minus 1, right? Or size, right? Because so if we think about this, if size equals 3, right? This is 1, 0, 1, 2, right? So this is size. Okay? So you want to take what's in size minus 1 and put it in size. I want to take what's in size minus 2 and put it in size minus 1. And I want to keep going until I get to the index that I'm trying to make a hole at. Right? So I'll start with size, and I'll keep going until I is, as long as I is greater than the place where I need the hole and go backwards. And I'll basically say elements at I equals elements at I minus 1, right? So this for loop will start at the end, and it'll pull everything forward, right, until I get to the index where I'm trying to make my hole. And now I can put my element in that hole, right? But there's one more problem with this implementation. This is almost right. What's going to happen if I keep adding and I keep adding and I keep adding? What's eventually going to happen to the space that I have? I'm going to run out. How will I know that I've run out of space and I need to recreate my array with more space?
If size is equal to your elements length.
That's right, exactly. So before I do any of this, I need to check to make sure that I've got space in my array. And the way I can check is I can say if the size of my list is the same as the length of my array, right? If that's true, then there's no more room at the end, right? We have to, we gotta make some more room and then copy everything over. So at this point, if that's the case, then I've got to reallocate a whole new array that's bigger than the array I have now, copy everything from the old array into the new array, and reset my elements instance field to point to the new array. This is going to happen, in a couple of different places. Oh, actually, no, it's just going to happen here. But so let's do that. So I need a new array, object array, bigger array, bigger elements, bigger array equals a new array. And now I have to decide, how big do I make this new array? I know how big the minimum size it needs to be is size plus 1, right? Because I'm already size, and I'm about to add 1 to, I'm about to insert something, so I'm about to become size plus 1. So I know I have to be at least size plus 1, but by making it just 1 bigger each time, I have to do this work every single time I add something new once I get past my initial size. So I might want to do something a little bit more reasonable, like, well, if I already made it this big, then it's, if they've already used as much space as I've given them, they're probably going to use about twice as much space, right? I can make that kind of heuristic guess, like, well, they're already 40 elements in my list, so I'm going to give them 80. And if they put 80 things in, well, if they're already 80, then maybe I'll give them 160. So what I could do is I could say, oh, you know what? Make it twice as big as my current size. Okay, so that creates the new storage, but now I have to copy from the old storage to the new storage. So I have to copy everything over. So for int I equals 0, I less than size, I plus plus, I have to essentially copy everything over. My bigger array at I equals whatever was in my elements array at I. And that'll just copy everything that's already in my elements array into my bigger array. And then at the very end, I need to swap my bigger array for my old array. So my old array was referred to by elements, and now I can just reset elements. I can say, oh, and now elements equals the bigger array. Right? So that will make my more room. Okay? So if I survive this, once I get past this, I know that there's room, in my array. So now I can pull everything over, right? So elements now points to the bigger array, and now I can use elements just like I did before. If there's already room, then that's okay. Then I won't do this. And I know there's room because the size of my current list is not as big as my array, so there has to be at least a little bit of room. And so then I can pull everything over and then put in the new element. And there's one last line of code I need here. So if I updated my elements by pulling everything over and putting something in, what else do I need to update? My size. My size is now 1 bigger. Right? So for remove is essentially the opposite. Now I never have to worry about resizing the array because I'm making it shorter. So whatever the array is, like, if I take something out of the list, I don't ever have to worry about the array being, too big for a smaller list. Smaller lists can fit into an existing array. So that part I don't have. But I do have to worry about pulling everything over, right? Pulling everything down. Just like we had to pull everything up in order to make the hole where we were adding, when we remove, we have to pull everything down. So here, I'm going to say, okay, my element t, right, the thing I'm removing, my element removed, is whatever was at that index. Now, we should really do this defensive programming here in order to make sure index is legal. And then once it is legal, then great, that's going to be right, so now there's a red squiggly line. And here is where that casting idea comes into place. Remember, we weren't able to make an array of t's. We were only able to make an array of objects. But we know that everything that we're storing here is going to be a t, right? So I need to return a t, right? And so that's why I have element removed. The type that I'm going to return, the type of thing that I'm going to then return is going to be this removed element, and it's type t. But the things that are in elements are of type object with a big O, because I couldn't make an array of type t. I could only make an array of type object. And so so the compiler thinks the thing on the right-hand side is object with a big O, and it says, hey, I can't reason about these types. Object does not have an is-all relationship with your type t, right? But I know that the things in there are type t, and so I know better, and so I can put a cast here, and now the compiler says, okay, as long as you're sure, I'll do it, right? And then we have to go from the index up to the size -1, right? Because we're pulling everything down, plus, and then pull everything down. So the things that were at elements I should be whatever was at elements I plus 1. So that'll pull everything down. Then I have to reduce my size by 1, minus, and then finally return the element that I removed. This one's easy. Get is simply make sure I have a valid index. If I do, return whatever is at that index. Now again, same thing. What's in the elements is an object of type O. What I'm expected to return is something of type T. I know that everything in there is of type T, so I can just say T. OK. And now we have a full implementation of list. Yeah.
So why do we use T if we could just use object?
Well, because when I use this list, right, I want to say, I want the type safety. If it's going to be a list of strings, I want to be able to say, give me a list of string, right? And then I want all of these things so that the Java can check the type safety, right? If I don't use that angle bracket T and just say object, right, then I have to define everything with respect to that generic object. And now somebody could create a list and start mixing and matching. I would have no way of preventing them from creating a list of objects and then putting a string in there, and then putting a scanner object in there, and then putting a triangle in there, and then putting a point in there, because those are all objects, right? Now, if you do want a list where you want to mix and match objects, you could still do this. You could just put object with a big O as that type T, right? But the idea here is that to the extent that we, have this ability to do type checking, we want to take advantage of that, right? All right. OK. Let's revisit set real quick, OK? If we look at the way we did set, OK? Set was a default where we added an element and then removed an element. What's wrong with doing set that way? Okay? The advantage of doing set this way is that as a default implementation, we don't have to worry about providing the actual code for set because we have a default implementation. But the disadvantage is that the specific implementation of the list might have a more efficient way of doing set. And in particular, for this array-based implementation of list, what's wrong with adding and then removing? What do I have to do to add? What do I have to do to remove that's inefficient?
You have to move everything over and move everything.
Exactly. If I use this default implementation with this array-based implementation, then what's going to happen is I'm going to move everything over, right? And then move everything over again. And it's like, and that doesn't make sense because, I know, like if I'm the array version of the list knows that, I can just replace the new thing from the old thing in that spot in the array without having to do that. So a concrete implementation can always override a default implementation by providing its own more specific implementation. So even though we have a default implementation, if we want to have a version of set that works more specifically for my array, I can override the one that I'm getting from the default. Now, here I see this override directive. That's exactly what that override directive is indicating. These directives with the @ symbols, they're never required in your code. They're just hints to the compiler that are saying, hey, this method is really part of implementing some interface, and so you need to make sure that there's some interface that this class implements that this method matches, right? And so I don't have to put that override part in, but I can say, okay, instead, I'll say public t sets. Let's see, what's the, how does this work? Yes. I'm just going to copy and paste. All right. So it's, right? And so here, I'm going to do a little, first I'll do a little array check, the index checking. And now I'll say, okay, old element is whatever was in elements index, right? And then elements index is going to equal the new elements, and then I'll return the old elements. And that's way faster, right? Way more efficient. And then here I have to do the cast, right? That's way more efficient than adding and removing, because at least for an array-based implementation, because I don't have to push everything over and pull everything back. And so here it's like, yeah, there's a default implementation, but I have a better way of doing it because I know I'm storing my elements in an array, and so I'm going to do it the better way. All right. So linked list is a different strategy for implementing lists. What it is it defines what you can think of as a node abstraction. And a node has two parts: the value at the node and then a pointer to the next node. And so a linked list looks more like this. So on the top, we have a diagram of what array list looks like on the heap. If I have an array list, then I have size and some pointer to some elements, right? And then that's my array of elements, some of which are filled, right? Some of which are null because I'm using only the first three. And let's say this is strings. It's a list of strings. So the first three point to a string, point to a string, point to a string. A linked list does it like this, where I also keep track of the size of my list. So a linked list has to keep track of the size of my list just like my array list does. But instead of having an array of elements, it has a head which points to the first node. And every node has a value, that's the element at that node, and a next pointer, which points to the next thing. And so a linked list, that's why we call it a linked list, because it links one node to the next. So that is the structure, that is the implementation you need to do for A4. And if you think about it, right, how do we insert something at a particular position? You have to walk the list. With the array list, I could just index into the array. With the linked list, if I want to get to the second thing or the fourth thing or the fifth thing, I have to start at the head and keep track of where I am and walk next, 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 and keep track of which index I'm walking to until I get to the spot in my chain. And if I want to insert something, I have to create a new node and fix up the pointers so that the new link is inside my chain at the right spot. And if I want to remove something, I have to walk to where I'm trying to remove and then fix up the pointers to take that node out. All right, so we'll talk a little bit more about the mechanics of linked lists on Tuesday, and then talk about the difference in performance between an array-based list and a linked list. But you can go ahead and start on your implementation of linked lists, which is due next Thursday.